Hello everyone, welcome to this lecture on Taylor and Maclaurin series. Again, I'm recording this for our class that we missed, but this obviously will be useful and it's going to be available on YouTube, so anybody watching this, the topic of this lecture is going to be Taylor and Maclaurin series. This is typically the third lecture in the power series chapter in a typical calculus 2 course, so you needed to at least be familiar with the concept of what a power series is and how to build representations of functions using a power series based on the function 1 over 1 minus x and its representation using a power series. But as we've seen in those previous sections, not every function can be reached or can be represented using a power series by constructing it or building it from the 1 over 1 minus x power series. So this is why we need a much more direct way, and this is what Taylor did, right? So Brooke Taylor came up with this concept, and he wanted to take any function f. So he wanted, if you give it any function f of x, he wanted to find a power series of the form summation from n equals 0 to infinity of c sub n times x minus a to the n. This is what he basically wanted to achieve. And he said, okay, what I need to do is, can I find a connection between the Cn and the formula of the function f of x? If I can find some direct connection between those two things, then for any given function, I can construct this type of power series for it. Notice this power series is centered at A. So there's different ways we say this. We say this is a power series centered at A. We also sometimes use the terminology about A. So you'll hear people use that. It doesn't matter how you approach that. It's either way, it's the same thing. Now that A could be any real number, but it could also be 0, of course. So that's a special case, as we will see. Right. So when you have this type of power series but centered at 0, it becomes it's referred to as a Maclaurin series, and I'll explain that a little bit later. All right, so basically what Mr. Taylor, and we went through this in class, so I will kind of go through this very quickly. He wanted to find these coefficients, and he wanted to find that connection. So he said, okay, let's actually write it in expanded form. So that's C0 times plug n equals 0 there, right? So this becomes C sub 0, x minus a to the 0, which becomes 1. So you get C sub 0 plus C sub 1 times x minus a plus C sub 2 times x minus a squared, and so on. C sub 3 times x minus a cubed, and so on. And then he said, okay, I'd like to know what this C sub 0 coefficient is. And he said, oh, there's a nice trick I could use. What if I replace x everywhere with a? It will wipe out all these terms except the C sub 0, and this side will be f of a. So f of a reduces to just C sub 0. So that's his first discovery, is that the first coefficient of this mysterious power series representation is f of a. So it's directly tied to the function that you're given and the center, which is fixed, right? So then he said, okay, how do I get this mysterious C sub 1? And the trick, and we've seen this before again, this is just a review, was to take the derivative and then plug in a. So if you take the derivative, this term disappears. This term becomes C1 plus 2C2 x minus a plus 3C3 x minus a squared, and so on. And if you plug in A everywhere, the left-hand side becomes f prime of A. The right-hand side, all of these terms will disappear except the first one. So you get a formulation for C sub 1. So again, now you always have to be careful with pattern recognition in mathematics. You always have to make sure you have large enough sample before you can make a conjecture about something and generalize something. So if somebody just looked at these two cases, they could easily surmise that, oh, okay, all these coefficients are basically just the order, if it's C sub 1, that's f prime, that means the first derivative, and you plug in A. Oh, maybe then C sub 2 will be like the second derivative and you plug in A. And the C sub 3 will be the third derivative and you plug in A. Well, if you guess that, it's not a bad guess, but it's not correct. You'll be close, but you won't have the correct exact answer. So let's do a couple more and you'll see what I mean. So if I do the derivative again, f double prime of x, so you derive everything in this, use the power rule. So this goes away. Here, this whole thing becomes 1. So you get 2c2. So now you start to see that things change. Then this becomes 3c3 and a 2 comes down. So we're going to write that as plus 3 times 2 times c3 times x minus a. And if you imagine there was another term here, the next term would have been 4c4 x minus a cubed, then the derivative of that will be 4 times 3 times c4 x minus a. Make sure I got my powers correctly. So this will be the second, and this next one will be the cube. Yeah, so the cube, yep, so I skipped one. So the cube would have had 3c3, and then that's squared. So this next one here, it's probably a good idea to write it down here. So let's go an extra term here. And I think make it easier so we don't have to guess. So this will be c4 x minus a to the power 4, but don't forget it's an infinite series, so you have to always end this sum with this ellipsis punctuation symbol. So if you take the derivative of this term, you get 4c4 x minus a cubed plus dot dot dot, and then this will be 4, and the 3 comes down, and you get 4 times 3 times c4 times x minus a squared plus dot dot dot. So now plug the a everywhere you see x. So everything disappears here, but what survives is 2c2. So this now tells you that c2 is not just equal exactly to f double prime of a, it's actually equal to f double prime of a divided by 2. So c2 is f double prime of a divided by 2. In fact, that 2 is really a 2 times 1, which is a 2 factorial, and this will become clear with the next one. So let's do one more and then you'll see the pattern. So if I do the third derivative, so derive all of these, this will disappear, this will become 1, so you get 3 times 2 times c3 plus 4 times 3 times 2 times c4 x minus a, and so on. So now you get to see what I mean. If I plug in a again, this will disappear, but what's left here is 3 times 2, and you can think of it as times 1 times c3. So now you get to see the pattern that c3 is going to be f triple prime of a divided by 3 times 2 times 1. So this here can be written as, can be thought of as 2 times 1. So now I can actually see what the pattern is. The pattern is f double prime of a here over 2 factorial, and here it will be f triple prime over of a, evaluated at a, that's important, over 3 factorial. So whenever you're solving for a certain c, there's a direct connection between the index of the c, the order of the derivative, meaning what level of derivative you're taking, first derivative, second derivative, third derivative, we call that the order of the derivative, and also what number you're taking the factorial of. So notice, going back to this one, I can actually now retrospectively think of this as C1 equals f prime of a over 1 factorial. And I can think of this as C0 is f0 of a, meaning the zeroth derivative. It's kind of silly, it's trivial, but means you don't take a derivative. And you divide by 0 factorial. Remember, 0 factorial as a convention is 1. So now you see the pattern. If it's a 1 as the index, then you have a 1 factorial and you have the first derivative. If it's a 2 as the index, then you have a 2 factorial and you have the second derivative. If you have a 3 there, then that's a 3 factorial and the third derivative. And this is what we just walked into, the same shoes that Mr. Brooke Taylor walked into when he discovered this. Although again, as I mentioned in class, historians have discovered that some of these results existed 300 years before Brooke Taylor claimed to have discovered them, right? Remember, Brooke Taylor is an English mathematician, and Colin Maclaurin is a Scottish mathematician. But historians discovered later that some of these ideas existed with Indian mathematicians around the 14th century, and they existed even in the Islamic Empire in the Middle East or in Baghdad around the 1300s. So it wasn't maybe formalized the same way we have it written these days in calculus books, but it's always important to keep in mind that the mathematics we see today wasn't just invented in Europe, wasn't just invented in United States, wasn't invented in Asia. It's a mixture. It's really a journey of many mathematicians building on previous mathematicians' work, and to refine the product, refine mathematics into the product that we have these days that we expect you to learn in 3 semesters of calculus, which is kind of amazing. I always tell my students, you know, it is always put things in perspective. The calculus you learn in the first semester, Calc 1, in a typical college course in the United States, that's typically a lot of the analysis or calculus that was built and put together and refined around the late 1600s into the up to maybe the mid 1700s, right? But again, keep in mind that a lot of these ideas were built on things that existed hundreds of years, or in some cases thousands of years before. Problem like the area under a curve was built on the area problem that existed 2,500 years ago, right? So when you really look at it, it probably was like stuff that was refined within maybe 100 years, and we expect you to learn that in 1 semester and understand it. So mathematicians, bright mathematicians who came up with a lot of these ideas and refined them, struggled with them for decades to come up with the results that we have these days. But they show up in a modern calculus book, they basically look like they're all like put together nicely and ready for you to learn. It's not that simple. Some of these ideas, even the mathematicians who came up with them struggled with them for a long time before they were eventually forged into the product that you see these days. So keep that in perspective. When if you struggle with Calc 1 or you struggle with Calculus 2, which is typically considered the hardest of the 3 courses, that's because, again, some of these concepts are not easy. And some of these concepts took hundreds of years for mathematicians to actually finalize and refine and construct. So if you struggle with them, or sometimes, God forbid, you have to repeat a Calculus 2 course or a Calculus 1 course or a Calculus 3 course, it's not the end of the world. Sometimes it may take you a little bit longer to master these concepts, and that's okay. Right? So, as I mentioned, Brooke Taylor is credited with coming up with these results, but again, a lot of the foundations were built well before that. He by the way, came up with this in 1715, right? And again, he relied on the work of many other mathematicians prior to his work. And then Maclaurin used his work to actually popularize the Taylor series centered at zero. All right, so what's the pattern? So the pattern is that we can generalize this to the C sub n is the nth derivative of f evaluated at a divided by n factorial. And once you know that, then I can go back to my top here, my top generic power series, and replace this C sub n with this formulation. So for any given function f of x, we're going to try to come up with a power series centered at a, and we can do that as long as we use the coefficients as the nth order derivative of f evaluated at a divided by n factorial times x minus a to the power n. So if you now expand that, then your C sub 0 becomes f of a. Your C sub 1 times x minus a becomes f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a plus, I'm gonna stagger these so I can fit it nicer, f triple prime of a over 3 factorial times x minus a. This should be a square and this should be a cube. And then once you go past the third derivative, we don't use the prime notation anymore, right? So we usually switch to numbers, Arabic numerals, and then we can put the fourth order of f evaluated at a divided by 4 factorial times x minus a to the fourth, and of course we keep going. So we're going to get eventually to the nth order derivative, so this is more generic way of writing it for any given term, and then this will be n factorial x minus a to the n, but don't forget it's an infinite series, so it shouldn't stop, so you always terminate it with the ellipsis punctuation symbol. All right, so that's a power series. Now, there are a lot of important theoretical questions here. So the key theoretical questions that the foundation that Brooke Taylor had to construct here, okay, coming up with a trick to find these formulas for how the coefficients are constructed is actually the easy part. he had now to answer a lot of questions about, can you always do this? Does this work for every function? Can we say that this function is exactly equal to this power series that you're getting? Right, so these are some of the questions that he had to answer, right? And these are very important questions. So first of all, we call this a Taylor series representation of f. And as we mentioned, we can say that this is about A or centered at A or at A of f at A, about A, or centered at A, or centered in A. So for the special case, where A is 0, for the special case where A is 0, what happens to this formula? Basically, rewrite it, but everywhere you see A, make it a 0. So your function f of x becomes summation n equals 0 to infinity, nth order derivative evaluated at 0, not A now, divided by n factorial times x to the n, because this A becomes 0, right? The A there and the A there becomes 0. And if you write it in expanded form, you basically plug in 0 for all the A's in this expansion. So f of A becomes f of 0 plus f prime of 0 divided by 1 factorial times x plus f double prime of 0 divided by 2 factorial times x squared, and so on. So you see what's interesting about this series? When you center it at A, the formula looks so much nicer. And what happened is a guy by the name of Colin Maclaurin Scottish mathematician, he was very inspired by the work of Brooke Taylor, and he took these Taylor series, but he liked using the version of these where A is always 0. So he focused on only using them with a center A equals 0, because it simplifies the formulation. The formulation is much cleaner when you do that. So, and then he wrote a book, a calculus book, in the 1700s, in around 1742, and the book became very popular. And since everybody started using Maclaurin's book, and talking about Maclaurin's book, and all the series that he used in his book were of this type, meaning they're Taylor series, centered at A equals 0, these type of Taylor series centered at 0 became known as the Maclaurin series. Right? So that's where the name gets attached to the actual type of series. But really, a Maclaurin series is just a special case of a Taylor series. It's a Taylor series where A is 0. So Maclaurin series is a Taylor series, but not every Taylor series is a Maclaurin series. Okay, so keep that in mind. So the superset is the Taylor series, and the special case is the Maclaurin series. All right, so that's where the terminology comes from. All right, so a couple important things, a note I want to mention here, and I won't write it down, but so we just showed that if f can be represented as a power series about A, then f is gonna equal to the sum of its Taylor series, right? So f will equal to the sum of this Taylor series right here. The question is, is that always true? Like, can you find a function that's represented by a power series that doesn't equal to its Taylor series? Right? So it turns out, yes, the answer to that question is yes, you can. You can find there exist functions that are not equal to the sum of their Taylor series. Okay, so what does that mean? That means you can actually construct a Taylor series that represents a function. So you can, if I give you some function f, you can build this kind of Taylor series like that. But this series does not converge to the value of the function. So it's not a one-to-one equality between the function and the series. You can build the series, but you can't really use it as a substitute for the function. So that's the key thing. That's the dangerous thing that you have to remember about Taylor series. You can always construct a Taylor series for any given function. All you have to do is just find all these derivatives. So you can build this up. The big question is this series that you're going to build up, does it converge to the formula of the actual function? And that's the part that's not always true. So you can actually always construct a Taylor series, but it's not necessarily always going to exactly match the function, meaning converge to it. Right? Because remember, there's a lot of stars that have to align when you work with a series. Your function is going to have some kind of domain, right? So for example, if I have a function 1 over 1 minus x, you can plug in anything you want for x, but you can't plug in x equals 1, right? Because it makes the denominator 0. If you can find a power series for that formula, is that power series always going to equal to 1 over 1 minus x? It depends on the radius of convergence of the power series. It depends when that power series converges, and if it does converge, then the sum should match the formula. And that's the big challenge with the series. Whenever you're using a series to replace a function, you have to deal with when does that power series converge, what's the radius of convergence, what's the interval of convergence, because that's basically your user's manual. That's going to tell you when can you get away with using that power series as a substitute for the real function. If you're using it for x values where it doesn't converge, then that equality between these two, the equal between the function and the series, this equal here is very delicate. It only is true if this part converges. If this part doesn't converge, you've got a problem with this equality. Because you're going to have one side that could be defined for an x value, but this side doesn't exist because it gives you something infinite, right? So this is the danger with Taylor series. You can always build a Taylor series for any function. I can give you any function, you can construct a Taylor series. But when does it exactly equal to the function? That depends on the type of function you're dealing with and depends on where that series end up converging, right? So that's the key thing. That's the key caveat that you have to remember. All right. So what we're going to do next is we're going to basically play around with constructing some of these Taylor series for some functions. So this is really the kind of problem or exercise that you need to become comfortable with when it comes to quizzes, homework, exams, etc. Right? So let's look at example 1. So example 1 says find the Maclaurin series. So remember what Maclaurin means. Maclaurin means A is 0. The Maclaurin series of the function f of x equals e to the x and its radius of convergence. Remember, the radius of convergence is basically a safety net that's going to come with this power series. It's a user's menu that says here's when you're allowed to use this power series, right? What x values you're allowed to use it with. All right, let's see. Let's switch color for the solution. So the first thing we need to do is we're going back to the previous page here. We're going to try to build this up from scratch. So a nice way to do this in an organized fashion is to actually make a little table, right? Or do it or format it in a way that's kind of like a table, organize it like that. So first of all, I need all these derivatives of the function. And then I need to plug the a into them. And if it's a Maclaurin series, then a is 0. Right? So that's what we're doing. So let's see how we can do this. So I'm going to make a little kind of table here. So this is solution. So make a little table here. And I'm going to, on one column, I'm going to put the actual nth order derivative of x, and then I'm going to plug the a in it, right? So keep in mind, Maclaurin means a equals 0, and my function f of x is e to the x. So this is going to be the nth order derivative evaluated at x, and this is going to be the nth order derivative evaluated at 0 because a is 0. So the first one is basically the case where n is equal to 0. So you could even kind of add like another column here that actually tracks the n values, but keep in mind we start with n equals 0. So n equals 0 means you don't derive at all, you take the actual function. So that's just going to be, so this is going to be f of x equals e to the x. Then next row is going to be f prime of x. Now what's that going to be? Well, it's going to be e to the x. What's nice about e to the x is when you keep deriving it, you're going to keep getting e to the x. So this is e to the x. F double prime is also going to be e to the x. F triple prime and so on. So we see the pattern. We don't really need to go any further. Sometimes, depending on the function and the formula you're dealing with, sometimes you may have to go like 5 or 6 terms to start seeing what the pattern is. But in general, you're roughly going to go maybe 5 to 7 terms max, right? So let's see. What are we going to do in this column? We're going to take all of these, but we're going to replace x with 0. So e to the 0 for all of these, so it's going to be 1. Right? So this is going to be f of 0, which is 1, f prime of 0, which is 1, f double prime of 0, which is 1, f triple prime of 0, which is 1. So now, when I go to write my Maclaurin series, remember what the Maclaurin series in general looks like. It's f of x equals summation n equals 0 to infinity, nth order derivative evaluated at 0 over n factorial times x to the n. And if you were to expand that, that's f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial x squared, and so on. So what are we going to do here? We're just going to plug in our specific values of these f of 0s and f prime of 0 and f double prime of 0. We're going to replace them with what we got based on our specific function we're working on. So your f of x becomes e to the x. So e to the x equals, What's f of 0? Well, that's just going to be 1. Plus, all of these are also going to be 1s. F prime of 0, F double prime of 0, F triple prime of 0. So what do you end up getting here? You're going to get 1 over 1 factorial times x. So you just get x over 1 factorial. So plus x over 1 factorial. If you hear snoring in the background, that's my dog. And then x squared times 1 over 2 factorial. So that's x squared over 2 factorial. Then x cubed over 3 factorial. And you keep going. So we found the pattern. So that's a Maclaurin series for e to the x. Now, when you find a formulation for a power series, it doesn't hurt to do what we just did and have an expansion, basically just the first several terms. But usually if you're going to do any other analysis on that power series, like for example, if you want to know the radius of convergence or the interval of convergence, you need to actually be able to write it in sigma notation, in summation notation, and actually know what the pattern of the terms looks like. So let's see if we can do that for this one. So what is the pattern? Well, this is summation n equals 0 to infinity. And remember, going back to this, the pattern, this is always 1, right? For all of these, it's always 1. So it's just going to be 1 over n factorial times x to the n. Or you can just write it as x to the n over n factorial. So that's the Maclaurin representation of e to the x, both written in expansion and in summation notation formats. So that answers the first question, which is give me the Maclaurin series. There's the Maclaurin series of e to the x. But then they said, give me the radius of convergence. Well, we've seen how to do that for power series in previous sections. We use the ratio test. So we're going to go ahead and do the ratio test. So I'm going to actually take this to the next page. Okay, and let's apply the ratio test. So first of all, what is my a sub n in this case? So this right here is playing the role of my, So this is playing the role of my a sub n. So a sub n for this series is x to the n over n factorial. Remember, a series is just, a power series is just a series with an x power in it. That's why we call it a power series, right? So this is still treated like a series, and this is the nth term of the series, right? So a sub n. So what would be the n plus 1th term, a sub n plus 1? You just change all the n's to n plus 1s. So this becomes n plus 1 factorial. Now remember, n plus 1 factorial on the side here is n plus 1 times n factorial. So that's going to come in handy when we reduce the limit. So we're going to do the limit as n approaches infinity, a n plus 1 over a n. And this becomes limit as n approaches infinity of, take the a sub n plus 1, so x to the n plus 1 over n plus 1 factorial times the reciprocal of a sub n. If you divide by something, you times by its reciprocal. So this becomes n factorial up on top, and then x to the n goes there. All right, to simplify this, let's break up certain things. So a couple things I can break up, and it's very important when you're doing the ratio test is that you go through all these steps and don't forget all these notations. If you try to do the ratio test without writing limits, it doesn't make sense. What you're writing is mumbo jumbo, that's not correct. If you leave out the absolute value, that's erroneous. So it's very important that all the details are included in your work, right? And always remember, in mathematics does not forgive. Whenever you use the equal symbol, it's sacred. So whenever you write down the equal symbol, you are saying emphatically that what you wrote on the left-hand side matches what's on the right-hand side. So every time you're writing any kind of work, always make sure you ask yourself that. So always double check, hey, what I'm writing down here, is it equal? Is it really equal, or is this something that is not always true? Maybe it's only true for certain x values and not all the x values, or certain true. And maybe one thing is the general rule and one is a specific example. They can't be equal, even if they relate to the same formula. So always remember, when you use the equal symbol, it's very important that you verify that both sides are truly equal. All right, so what can I do with the x to the n plus 1? I can write it as x to the n times another x times n factorial. And in the denominator, I can write the n plus 1 factorial as n plus 1 times n factorial times the x to the n. And this exposes things that I can cancel. I can cancel out the x to the n's. I can cancel out the n factorials. So what's left is going to be the limit. And this is the part where you have to make sure you don't rush and make mistakes. It's very easy when you're doing the ratio test, when you get to this stage, to get kind of excited. Oh, I canceled a bunch of stuff. So, okay, now I can do the limit. And you rush through that step and you make a mistake. Or you leave out something, right? So always be careful. So what's left over inside the absolute value? There's the x on top, and there's the n plus 1 in the denominator. So I have an absolute value of x over n plus 1. But it's important to remember that when you have an absolute value of a ratio, you're allowed to split it. You're allowed to split it into the absolute value of the top and the absolute value of the bottom separately. You cannot do that with a sum. You cannot do that with a difference. But you can do that with a product or a quotient, right? You can separate, split an absolute value. So this becomes limit as n approaches infinity of absolute value of x divided by absolute value of n plus 1. But remember, n is positive. N is an integer, right? So this is going to be, n is a positive integer starting from 0 and going to infinity. So the absolute value is just going to be n plus 1. One more interesting step is when I'm taking the limit is only concerned with any term that involves n. So this absolute value of x is not relevant to the limit really. So, and it's multiplied, you can think of this as a multiplication, absolute value of x times 1 over n plus 1. So because of that, I can take the absolute value of x and I can take it out of the limit process and move it outside of the limit process. Times the limit as n approaches infinity, 1 over n plus 1. And now I can just concentrate on doing the limit. So the limit as n goes to infinity of 1 over n plus 1 is just 0. So no matter what x is, as n goes to infinity, this is going to be absolute value times of x times 0, which is always 0. Which means it's always less than 1, which means by the ratio test, this power series is always absolutely convergent, hence convergent. So power series is, so I should say, by the ratio test, power series is convergent absolutely, or absolutely convergent. And hence convergent for all x. So what does that tell you about the radius of convergence? The radius of convergence is infinity. What's the interval of convergence? Well, all x means the whole number line from negative infinity to infinity. So the interval of convergence, they didn't ask for that, but it's a bonus. Negative infinity to infinity. So if I draw my number line, little visualization of this, here is it's centered at 0, and the convergence stretches for all x values to the right of that and all x values to the left of that. So that's negative infinity, infinity. So if you think of this as like a circle that you're drawing like that, the radius of that circle is r equals infinity. That's the radius of convergence, right? So that's the stretch of x values away from the center across which the convergence is still okay. So what does that mean? So this is very powerful for e to the x, because this is telling us that this power series, this Maclaurin series that we found for e to the x, not only we can assume it equals e to the x for certain x values. No, it turns out that we can use it for any x value. So no matter what x is, this expansion is always going to converge to this formula. Always. So this is why this is one of the most used power series out there. Because e to the x shows up in pretty much all the mathematical applications and engineering applications you work with. And being able to substitute this power series makes it a lot easier for you to work with that instead of e to the x. Especially if this features inside another much more complicated formula, right? So this Maclaurin series is really a good one because you can use it no matter what x is. So you can use it and assume it equals e to the x no matter what x is. Now here comes the catch. Is that, so this is where I can show you that we can go to the website here. So mathmatters.net, and we can go to Explore Tools. Sequences in Series Explorer, and I'm gonna have to make this slightly bigger so we can see it better. So let's go to Power Series, and let's go to this like interactive visualization of Power Series. Sorry for scrolling fast. When I get to it, it's right at the bottom there. Actually, I could use the menu. There's a menu to go there. So here is here is my function e to the x. Now remember what we just said. We said that it's equal to this. 1 plus x over 1 factorial, x squared over 2 factorial, and so on. So is it equal? Well, it depends how many terms of this series you use. If you only pick a first few terms, then it's not going to be exactly equal. It's going to be just an approximation, right? And it's centered at 0, so that approximation, as long as you stay close to 0, is going to be better in that region than the farther out you go. That's if you only chopped it. You didn't decide to use every single term. If you use all the terms, that's the caveat. If you use all the terms, which is infinitely many terms, then this whole thing is exactly equal to e to the x. But if I decide, hey, I'm only going to use this term, and this term, and stop there, then this becomes a squiggly equal symbol. This becomes approximately equal. So this little interactive thing here, it allows you basically to kind of see how the approximation improves the more terms you add. So right now, so let's start with one term. So the red graph is the actual exact function, e to the x. The green graph is just the first term of the power series, so which will be y equals 1. So you notice they only match, they only have the same y value at 0, at the center, right? But if you go beyond the center, then the green line and the red curve are far apart. And the approximation gets further, gets worse and worse. The gap between them gets bigger and bigger the farther out you go from the center of the power series. That's why picking where the center of the power series is very important, right? So if you want to use a power series approximation of a certain function, it's always useful to localize and center it carefully to the area of x values that you want to focus on, right? But for many cases, a Maclaurin series, a typical series centered at 0, will do the job for you, right? And that's why it became very popular. So watch what happens when I increase the number of terms. So if I add one more term, what does that mean? That means my approximation becomes 1 plus x. So look what happened to the green graph. The green graph now hugs the red graph a little bit better either side of 0. But as you start to stray away, again, the approximation gets worse and worse. But you can fix that by adding more terms. So if I increase the number of terms to 3, so now look, it's getting farther out. So there's almost a perfect match from negative 1.2, x value equal negative 1.2 to 1.2. You're having a very good approximation. And that's only just using the first 3 terms. So in real life, engineers, when they do this, they obviously can't use an infinite number of terms. So they have to decide where to chop it. And this kind of analysis helps them understand if that number of terms is good enough for the approximation that they want to achieve. And if they realize, hey, that's not accurate enough, the error is too large, then they can pick more terms, add another term. So you can go up to the 3rd order term or the 4th order term, meaning the 4th power or the 5th power or 6th power and so on, right? So you chop it at a specific power based on how close you want to get. And the more terms you add, the wider the away from the center you go. You hug the curve. So if I go, so watch what happens if I go 9 terms. Look at that. You don't even see the red graph because they're identical for this interval that I use, which is from negative 2 to 2. Now, of course, if you go way farther out than that, you're probably going to see that they diverge or they get away from one another. So they're going to have some kind of error margin. But you can see just with 9 terms, so power 0, power 1, power 2, all the way to power 8, you're getting a very good approximation. All right, so this actually leads me to another very interesting question that comes up, because this is important when you want to use an approximation, is you always want to keep tabs on the error margin. So the question that engineers and mathematicians ask themselves when they use a power series to approximate a function is, how can I know roughly what the error margin is from the truth based on the choice of how many terms I'm going to pick? So instead of usually deciding the number of terms or knowing the number of terms to pick and then try to measure the error, usually in the real world, when you're an engineer or scientist, you know what error margin you want to achieve first. So that's the part that you're given. That's the part, and sometimes that's a norm in your company, like your firm, your engineering firm would have some certain norms, certain rules. Like, okay, for these kind of calculations, we stick to 5 decimal places, or these kind of calculations, we stick to 9 decimal places accuracy, right? So these are things that are kind of set in advance. So then the question becomes for you in practice is, if I know what error I want to stay within, how can I figure out how many terms it's going to take to achieve that? And that's a very interesting question. Well, it turns out the gap, the error, can be approximated by the next term. So if you stop after 8 terms, or you stop at power 8, you can take the power 9 term, and if you compute that, that will give you a rough estimate of how far away you are from the truth. So that's called the remainder term, or the remainder of the approximation. Right? So we're going to see a little bit more about that later. But for now, keep in mind that in practice, we don't use all the terms, we use an approximation, and we have to make a decision, we have to make a judgment call based on what accuracy we want to achieve. All right, let's keep going. So that was an example just to kind of get us started. Now let's take a look at a very important theorem that we're going to mention here. So, and this ties to exactly what we just talked about. So, if f has derivatives of all orders, when is it true that f of x matches its Taylor series? So that's really a vital question that we keep coming back to, right? Well, again, what this means that the limit of the sequence of partial sums. You guys remember the sequence of partial sums? Capital SN. Is f of x. Right? So if I want to say that, hey, f has derivatives that exist doesn't matter. You can keep deriving it, and every time you derive it, you're going to get a derivative that makes sense, that's defined, right? So for example, e to the x, if you keep deriving it, you keep getting e to the x, and e to the x is always defined. So that's called a function that's differentiable everywhere, right? And it's infinitely differentiable. So you can keep deriving it as many times as you want, right? So the question is, assuming that that's the case, meaning you don't have that bottleneck of trying to find the derivative, you can find the derivative for the function, whether it's the first or second or third or fourth, you can keep deriving it. When does this match this? Well, we want this to converge and its sum to equal that. What does it mean? Remember from the chapter on series, what does it mean for a series to converge? A series converges if its nth partial sum, as n goes to infinity, converges. And whatever the nth partial sum converges to, that's going to be the sum of the whole series, right? So by saying that this equals to that, I'm saying that the nth partial sum of this, if I construct the nth partial sum of this, its limit should give me that. So what would be the nth partial sum of this? Well, the nth partial sum, the way we labeled it before when we talked about series, was S sub n. But if you work with the Taylor series, we call it T sub n. So the nth partial sum is T sub n of x. So what is T sub n of x? T sub n of x is basically this summation, but I'm not going forever. I'm going up to the nth term and stop it. So this is going to be summation from I equals 0 to n fi of a over I factorial times x minus a to the I. Now if that looks confusing, let's write in expanded form. It basically means you're going to have your f of a, you're going to have your f prime of a over 1 factorial times x minus a. You're going to have f double prime of a over 2 factorial times x minus a squared, dot, dot, dot. But you're not going to go on forever. You're going to stop at the nth term. So the nth power. So that's T sub n. So in order for this power series to converge to that, I want the limit of T sub n, limit of this summation. When I make the n go to infinity, what does it mean when I make the n go to infinity? That means I'm expanding this to all the terms, not just stopping at the nth term. Then I want that to have a limit that matches the function. So saying that the function is equal to this Taylor series means that limit as n approaches infinity of Tn of x is equal to f of x. So this is like our S sub n when we talked about nth term or nth partial sum. But when it's an nth partial sum of a Taylor series, they like to use the letter T for it. Right? So this is what T sub n is. T sub n is basically going all the way to the nth power and stopping at the nth power. So you don't go on forever, you just stop at the nth power. Now, if you stop, remember that means you don't have the exact value, right? So whatever this part is going to be, there's a gap between this summation, this T sub n, and the truth, and the exact total sum. So if you think of the total sum as some sum s, then the sum s is going to be Tn of x plus some kind of remainder, Rn of x. So there's some kind of missing remainder. That's the gap between the nth partial sum and the total sum. And the total sum is it's gonna have to be your f of x. Right? So this has to converge. If you stretch it, if you make this n go to infinity, what happens if you make n go to infinity? This stretches to fill the whole thing, to fill the infinite sum, which means as n goes to infinity, this stretches to fill the whole sum, and it will match my function, and the Rn, the remainder, will shrink to 0. Okay. So that's the interesting relationship between the T sub n and the R sub n. When one grows, the other one goes down. But that R sub n is good to help you gauge how far away you are from the truth, right? So this is an error term. And this here is called a Taylor polynomial of degree or order n. Why? Because because it's chopped, right? So it's not infinite, so it looks like a polynomial. And the highest power of x that shows up is going to be x to the n, so it looks like an nth power polynomial. Right? So, and it's coming from a Taylor series, so we call it a Taylor polynomial. All right, so let's write a little theorem that kind of ties these things together, and then we'll look at another example. So theorem: if f of x is equal to t sub n of x plus r sub n of x, where t sub n is the nth degree Taylor polynomial of f at a, and the limit as n goes to infinity of the remainder term is 0. So the remainder shrinks to 0 as you expand that Taylor polynomial to stretch the n to infinity, for absolute value of x minus a less than some radius of convergence r, then f is equal to the sum of its Taylor series on the interval absolute value of x minus a less than r. So what this is basically saying is saying that if you can write the function as our Taylor polynomial plus some kind of remainder, and you know as n goes to infinity this remainder is going to shrink to 0, then that tells you that the limit of this Taylor polynomial is going to match the function as n goes to infinity, which means the function is represented by the Taylor series, right? Over whatever interval of convergence you're working on, of course. So this is conditioned by where the convergence happens, for what x values it happens. So there is something called the Taylor inequality. And this is very useful for getting a sense of what the error margin is, right? So here's what it says. So if absolute value of the n plus 1th derivative of f of x is less than or equal than some number m for x minus a, an absolute value less than or equal to d, then the remainder Rn of x of the Taylor series satisfies the inequality absolute value of Rn of x is less than or equal than m over n plus 1 factorial times the absolute value of x minus a to the n plus 1 for absolute value of x minus a less than or equal to d. All right, so this one sounds really confusing, so let me box it up and let's explain it in plain English. What is it really saying? I'm gonna try to explain it in simple terms. So in simple terms, what this is saying, remember we said that the function, if it's represented by a Taylor series, then it should be equal to the Taylor polynomial plus some gap, some remainder. Right? And we said this gap is really the error margin to the truth. Right? So that's really the gap between when you chop it, when you pick just the first few terms, how far off are you? Well, Rn is going to be f of x minus t sub n. So this is your error. Your error is the gap between those two. This theorem, and you don't have to prove this theorem, we just take it for granted because somebody else had to work hard to prove it. We don't have to prove it. We just accept the result and use it. This says that this absolute value of this remainder, that gap, that error margin, you can find it or you can cap it by using this inequality, by using this formula. So you don't know exactly what it is, but you can find an upper bound for it. And you may recall we've done something similar to this when we did the trapezoidal rule and Simpson's rule. So even though you don't know how far away you are from the truth, there is an inequality that can give you a rough idea. It gives you an upper bound on your error, so you know you're within a certain error, right? So at least you can find your bearings, right? You don't know the exact error, but you know an upper bound for the error. That's what this inequality is saying. It's saying that error that we don't know, you can compute this part right here, and it will tell you roughly you're within that error margin. So let's use a concrete example. Remember the one we did earlier with the exponential? This right here. So let's say you decide, I'm going to use the first three terms. But you don't know how far you are from the exact, how good of an approximation that would be. So if you went to the second power and you stopped at the second power, the gap that's left over, this becomes your Rn. If you stopped at T2 of x, if you stopped at the power 2, this becomes your R2 technically. R2 of x. So that's your error. But you don't know what that error is because the error is an infinite sum. So how are you going to compute exactly what that is, right? You can't compute it. So that inequality is a lifesaver because it says, I can't tell you exactly what that error is, but I know that you can cap it. You can take the absolute value of that error and you know it's going to be less than m over n plus 1 factorial, so that'll be 3 factorial, times the absolute value of x minus a, which in this case will be just absolute value of x, because a is 0 here, because it's a Maclaurin series, to the power n plus 1, which will be 3. And all you need to know, to get this number here, you need to know what this m is. So where do you get the m? Well, they said m is just an upper bound for the n plus 1th derivative of f of x. So in our case will be the third derivative of f of x. And you have to find an upper bound for that over the interval absolute value of x minus a, which again will be absolute value of x in this case. And you have to pick some interval. So you have to decide on what error margin, how far away you're going to go, right? So let's say I decide I want my absolute value of x to be less than or equal to 1. So that's how you pick your d. That means I want to only stray away 1 unit either side of 0, my center. Then, based on that, you compute the third derivative, which by the way in this case will be just e to the x, and you ask yourself, if I graph the function e to the x just between -1 and 1, e to the x is going to look something like that. Find an upper bound for that. So find the highest y value that function, that curve reaches. Well, and call that m. So that will be m, and notice it happens at 1. So m in that scenario would be f triple prime of 1, which will be e to the 1, which will be just e. So I could use that as my m, and I can plug it in here, and this will give me an upper bound for my margin. Now the x, again, depending on what interval you're working with, you can pick a certain, this is the error margin. Here, this will give you the absolute value of x cubed. You can write it as less than or equal to this, right? You can use this. So absolute value of x is less than 1. So this is going to be less than or equal than e to the 1, which is the m, over 3 factorial times 1. That's your d. So by just doing this, I now have a number that I can use, and that tells me, so let me actually compute that. So e to the power 1 divided by 6. So that's going to be roughly 0.41. So that gives you a rough error margin between you and the exact value of the function under the circumstances you picked, which in our case means if we just use the first 3 terms, then we expect our y values to be within this error margin of the true value of e to the x, as long as you stay in the interval -1 to 1, right? So we had to set that first, right? So this is a very useful tool to help you find and cap roughly on your error. And this is useful to gauge, based on how many terms you picked, how far away you are from the truth. Even though you can't exactly find that error, you can at least find an upper bound for it. All right, so that remainder inequality is very important in practice, right? All right, let's see here. I want to check real quick the time. So this, yeah, I don't want to go beyond our lecture. So our lecture is a couple hours usually, 2 hours and 5 minutes. So I'll just do that. Again, as you're watching this, of course, you can always pause, rewind, watch it as many times as you need to, and go over things carefully, look at the notes, look at the website for additional help. Again, this is one of those chapters that's typically the hardest chapter in Calc 2, so it's very common for students to struggle with this chapter, but it's one of those things that by working at it and going over it a few times, it will start to click and make more sense. And of course, you can ask me if you have any questions. All right, so there's some key things there we just looked at. So let's see what other results are interesting here. All right, let me see here. I want to skip a couple things. I had another example in the notes, which is example 2, but that's actually related to what I just did. the error margin, the calculation, stuff like that. So I'm going to skip that one. The other interesting follow-up here, we discovered a Maclaurin series for e to the x, and like we said, it was summation n equals 0 to infinity x to the n over n factorial, and this is one of those formulas that you need to memorize. We showed you how you can build it from scratch, but it's a pain to do that every time. So you're gonna get to a point where it's better to memorize it, and it's actually the pattern is so easy to kind of memorize once you write it a few times. So it's 1 plus x to the 1, and then the power matches the number that you're going to take the factorial of. So 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. And you keep going until you get to x to the n, but you don't stop there, because if I stop at x to the n, that's t sub n. That's not the Taylor series. That's the Taylor polynomial of degree n. So be careful. The distinction is very important between a Taylor polynomial and a Taylor series. One is infinite, one is chopped off, like it's a finite number of terms. So this goes on forever. So the one other cool thing I'm going to show you here, what if I replace x? So this is, we said, so remember what we said. We said this is true no matter what x is. We proved it, right? So, Dexter, stop. So we proved it. We showed that this is always true no matter what x is. So this equality is true. So what if I try some x value? So what if I plug in x equals 1? Let x equals 1. So if I let x equals 1, the left side becomes e, and the right side becomes 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. Guess what we just discovered? We discovered a series that converges to the number e. This series converges to the number e. Which means if I use like the first few terms of this series, depending on how fast it converges, I'm probably going to get a decent approximation of the number e. All right, so this is an interesting follow-up or result from obtaining this Maclaurin series of e to the x. But of course, a Maclaurin series is centered at 0. I could have constructed a power series of e to the x that's centered somewhere else. It doesn't have to be centered at 0. So it would have been a Taylor series, more broadly, centered at some other number. So I think I do that in the next example. So let's do that. Example 3. Find the Taylor series for f of x equals e to the x at a equals to 2. So please keep in mind a very important caveat. Whenever they ask you for a Taylor series, they have to tell you what a to use. But if they ask for the Maclaurin series, they're not going to tell you the a because they assume you know that a is 0. Right? But the Taylor series, they have to tell you specifically what a value to center it around. So here they tell you a equals 2. So one thing that's, again, interesting is that there's certain things that don't change here. My derivatives are not going to change. So when I make my table, that part is not going to change. And I'm going to, now that you've seen it the first time, I'm going to make a slight modification. So here I'm just going to put 0, 1, 2, 3, 4, 5, right? Here I'm going to put fn of x. Remember that n is not an exponent. When you put parentheses around it, that means that's the nth order derivative of f of x. So this is where I find all the derivatives. So the first one is the 0th derivative, means it's actually the function f of x. So this is just e to the x, and then you keep deriving it. So e to the x, e to the x, e to the x again. This is a silly function kind of, because it always gives you the same thing. But then here comes the part that will be different from the previous time. This time we're not plugging in 0, we're plugging in the a value they gave us, which is 2. So all of these are going to be e to the 2. So when you go to write the Maclaurin series, the Taylor series, I always like to write the generalization first and then plug in the pieces that we have based on the problem. So the general formula is, for a function f of x, it's going to be fn of a over n factorial times x minus a to the power n, right? So what's going to happen for our case? For our case, it's going to be e to the x still, but it's going to be summation n equals 0 to infinity fn of 2 over n factorial times x minus 2 quantity to the n. So that's the Taylor series centered of e to the x centered at 2. And we could, of course, write the expansion of it, right, the first few terms. So if I expand it, what would that look like? Well, what are you going to replace this with? No matter what n is, this is always going to be e squared. Now, of course, keep in mind that's kind of particular to e to the x. That's not going to be true with other functions and other examples we're going to see. So the first term is going to be 1 plus, so first of all, why are we getting 1? Because you replace n with 0, so 0 factorial becomes 1. The 0th derivative of this will be e squared. No, so I should say that's e squared. But then you're going to multiply by x minus 2 to the 0, which is 1. So this is going to be e squared. Plus, the next one is going to be e squared over 1 factorial times x minus 2 plus e squared over 2 factorial times x minus 2 squared plus e squared over 3 factorial times x minus 2 cubed, and so on. So that's what this Taylor series of e to the x centered. So this is e to the x. That's what it looks like. This right here, by the way, I should actually plug in e squared, since we already know what that is, so we can hard code that in there, because it has changed for all of them. And this is the expansion of it. All right, let's do something different. So let's do Maclaurin series for sine x, right? And prove that it represents sine x for all x. Okay. All right, so I'm gonna go ahead and flip the page here in case you're ready. And this will be example. So remember, I skipped example 2. Yeah, double check what number. So we did example 1. And I call this one example 3 because example 2, I skipped that one. Example 4 is find the Maclaurin series of, or for sine x Now notice they don't have to tell you what A is because Maclaurin means A is 0, right? So you're supposed to know that. And prove that it represents sine x for all x. All right, so we know how to construct the Maclaurin series. We know the mechanics of that. How are we going to prove that it's always going to represent sine x? So there's a couple ways you can do that, but let's go ahead and go through it. All right, so the first thing we're going to do is make our little table. Keep in mind that we're dealing with sine x, so you need to remember your trig derivatives. So n is going to be 0, 1, 2, 3, 4, 5, 6. It's actually not going to take that many before you start seeing a pattern. This is going to be the nth order derivative of f of x. So the first one is going to be what? It's going to be sine x. You just copy the function. But after that, you're just going to keep deriving it. That's what you do in this column. So what's the derivative of sine is going to be cosine x. What's the derivative of cosine is negative sine. What's the derivative of negative sine is negative cosine. Derivative of that's going to be sine. Derivative of the next one is going to be cosine. Derivative of that, you get negative sine x. Now, you probably notice that there's something repetitive here. It goes sine, cosine, negative sine, negative cosine, and then the cycle here repeats again. So if I go one more here, the derivative of that will be negative cosine, and you can see that that cycle for functions repeats itself. So this is very useful because this tells you that there's a pattern that's going to keep repeating, and it helps you know that after the fourth pattern, after the fourth term, you'll know what the next four will look like. Right? At least you know what the derivative is going to look like. All right, the other thing to keep in mind is that we're doing a Maclaurin series. So Maclaurin means A is 0. So here we're going to do the nth derivative evaluated as 0. So you're going to actually plug 0 into all of these. So sine of 0 is just going to disappear. Cosine is going to give you 1. All the signs are going to disappear. Cosine here is going to give you negative 1 with the negative in front of it. And then 0, and then 1, 0, and then negative 1. Interesting. So let's write the formulation in general. So in general, for a Maclaurin series, it's summation n equals 0 to infinity fn of 0 over n factorial times x to the n. You don't have a minus a anymore there. So what would that look like? All right, sorry I had to pause for a minute because my dog's barking and they might bark again, so I apologize in advance. All right, so let's see if we can use this, and we're going to plug in these patterns. So first of all, our function is sine x. And if I write the expansion of this, remember what the expansion of that would look like. It will be f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared. This is the same one we use for the e to the x Maclaurin series. Plus f triple prime of 0 over 3 factorial times x cubed, and so on, right? So we're going to actually use this pattern, but we're going to substitute our f. This is our f of 0. That's our f prime of 0. That's f double prime of 0, and so on. F triple prime of 0. So we already see that after the first 4, these are going to repeat. So this is going to be 0. That's going to disappear. That's not going to show up, right? But this one will be a 1. So you're going to end up with just x over 1 factorial. So you're going to have 0 plus x over 1 factorial. Then the next one is a 0. So this is going to be another 0. So meaning you're not going to have an x squared term show up. But then the x cubed term is going to show up with this becomes a negative 1. So it becomes minus 1 or minus, yeah, let me write it like that. So minus 1 over 3 factorial x cubed. Now, this is the fun part. The fun part here is that we know that the next 4 numbers are basically a repeat of the previous numbers. So the power 4 term is going to be 0, so that's not going to show up. But the power 5 term is going to show up with a 1 on top. So this is going to be plus 0 plus 1 over 5 factorial x to the 5th. Then plus 0 minus 1 over 7 factorial x to the 7. And so on. So we get that cycle to keep repeating. And you see a very interesting pattern. If you focus on just the terms that survived, so get rid of all the zeros, what we have is x over 1 factorial, which is just x, then minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7 over 7 factorial. And I can already see a recognizable pattern. What's the pattern? The pattern is I have an alternating series, so the sign switches back and forth between plus and minus. And the powers are all odd. I don't have any even powers of x. So I can guess what the next one is going to be. It's going to be a plus x to the 9 over 9 factorial minus x to the 11 over 11 factorial, and so on. So that's the Maclaurin series of sine. Now, remember, just because you can build it, it doesn't mean it actually converges to that function. It equals to that function. So this is where this part is interesting here. They said prove that that summation you just came up with actually converges to sine x. So how are you going to prove that? Well, we can prove it by using what we just learned. Find the remainder, see if we can find an upper bound for the remainder and show that this converges to 0. Because if this converges to 0, then the remainder converges to 0, then our expansion converges to the function, right? So that's how we're going to do this. So, since fn plus 1 of x, what would be the n plus 1th derivative? Well, we don't know whether that's an even or odd. So it's going to be either a sine or a cosine or a negative sine or a negative cosine. Because we know it's a 4 cycle, right? So it keeps repeating those. So it doesn't matter where. So if you pick like some random nth derivative or 100th derivative or the 10,000th derivative, you're going to either get sine, cosine, negative sine, or negative cosine. So that's plus or minus sine or plus or minus cosine. We don't care which one it is. What matters is the absolute value of that is always less than equal to 1, which means we can let m be 1. Remember, our m from the inequality is supposed to be an upper bound for the n plus 1th derivative. So when I go back to that inequality we had earlier, I already know what to replace this m with. So my remainder is going to be less than 1 over the n plus 1 factorial times x minus 0 to the n plus 1. So for the sine function, our remainder is going to be less than m over n plus 1 factorial times absolute value of x minus a. I'm just going to write the generic formula first. So in our case, a is 0 and m is 1. So our remainder, which by the way is positive, is going to be less than 1 over n plus 1 factorial times absolute value of x to the n plus 1. Now what happens if you take the limit of this? We can use the squeeze theorem. If I take the limit of this part as n goes to infinity, what happens to this part? Well, this part goes to 0, and this whole thing actually goes to 0. That's a theorem, by the way. I didn't mention that earlier. Yeah, I should actually mention that result. So you can prove, when we did the theorem where we talked about so there is a side theorem, so I'm going to mention it here. Limit as n approaches infinity of absolute value of x to the n over n factorial is equal to 0 for every real number x. That's the result. There is a proof to it. We won't bother with going over the proof right now, but that's a result that you can take for granted. There's several ways you can prove this. There's some cool ways you can prove this, but whenever you see a pattern like this, when n goes to infinity, this is going to go to 0, right? One way to do it is you can split it up and you can do an inequality, but we won't go through that right now. But just take my word for it. This limit is 0, which means this limit here, which is really the same thing, but n is shifted to n plus 1, will also go to 0. So limit as n approaches infinity of absolute value of x to the n plus 1 over n plus 1 factorial is equal to 0. Therefore, by the squeeze theorem, if this part goes to 0 and this side goes to 0, then what's in between is going to go to 0. Limit as n goes to infinity of Rn is also going to be equal to 0. Which implies limit as n goes to infinity of Rn goes to 0. If the absolute value of something goes to 0, then what's inside goes to 0. So what does that tell you? Therefore, sine x is equal to the sum of its Maclaurin series. Because if the remainder shrinks to 0, then the Taylor polynomial, or the nth partial sum, expands to fill the function, to reach or converge to the function. Alright, so actually the result from this is something that, again, we can also memorize, that comes in handy. Just like the e to the x Maclaurin, representation. Sin x is one of those that you're going to come across a lot in engineering applications and physics and other sciences. So it's one of those that you really need to memorize. So you don't have to go through this go through what we just did to construct it, although you can construct it. Like all it took is just we constructed this table and we're quickly able to come up with the pattern, right? So if you're asked about, like, if I ask you in an exam to give me the Maclaurin series of sin x, you can do it from memory or you can do it by building it from scratch like this, right? So you have options, right? It's easier if you memorize. We're going to get you a table later of certain Maclaurin series that are recommended for memorization. E to the x is one of them, sine x is one of them, cosine is one of them. There's a ln one, there's a arctangent one. So there's a few of them that it's worth memorizing them. It saves you the pain of having to actually reinvent the wheel every time you need to use them. All right, so sine x has a nice pattern. Starts with x and then x cubed over 3 factorial. But then plus x to the 5th over 5 factorial, minus x to the 7 over 7 factorial, plus x to the 9 over 9 factorial, and so on. So that's the Maclaurin series representation of sin x. Now, by the way, this is actually always convergent, which is kind of interesting, right? So it's true for any x. One thing I haven't shown you yet, how would you write it in closed form? This is actually a good exercise for you to pause the video and see if you can write it on your own, and then resume the video to see the answer. Basically what I'm asking is, write that formula, write that pattern in summation notation. So what formula would you put in there for your a sub n that when you expand it, it gives you these terms? So pause the video, think about it, see if you can come up with a formula, and then resume. All right, so let's see. So I want the sign to switch back and forth. So I need the -1 to the n term. And when I plug in 0, that's going to be 1, so that gives me positive. And when I plug in 1, I get negative, and then 2 gives you positive, so it matches the right order, plus, minus, plus, minus, plus, right? Then what else do I need? Then I have all the powers of x have to be odd numbers. If I want the powers to be odd numbers, I can just put x to the n, because this n goes from 0, 1, 2, 3, 4, 5. I'm going to get the even powers to show up. I don't want that. So if I want to make sure that for these values of n, I end up with only the odd powers, I could use a 2n plus 1 pattern or a 2n minus 1 pattern. That's what guarantees that what comes out is an odd number. Then, the denominator, notice what you're taking the factorial of, matches the exponent. So that's the easy part. So this will be over 2n plus 1 factorial. Now, this is always the tricky part, coming up with the formulation. So always test it. And when you test it, don't just verify the first 2 or 3 terms. You really want to go far enough. So let's plug in 0 here. If I plug in 0, this will be 1. This will be x to the 1 over 1 factorial. And that gives me the perfect match with the first term. If I increment the n to 1, this becomes a negative, so I get a negative sign. If I put a 1 in for the n, this becomes a 3 over 3 factorial. So that's a match for that. Then plug in 2. This becomes positive 1, so I get a positive. This becomes a 5 over 5 factorial. Plug in 3. So this becomes odd, so I get a negative. And then this becomes 7 factorial. So I can see it works, right? So always verify these formulations. And this is true for all x. Now I could have verified that also by doing the radius of convergence. So if you did the ratio test to this, you'll find that it's always convergent, no matter what x is. Right. All right, let's see. I think I want to show you maybe a couple more examples, and that's it. And then we'll wrap things up. Maybe, so we just did sine, we'll do cosine, and then we'll do another one, maybe a couple more. Yeah, let's do that. And then that should take care of it. So I don't want to make this any longer than it is. Let me check. Yeah, I'm already kind of over in terms of time, but I want to wrap up this section. All right, so let's do, what's the next example I want to do here? The next example is the Maclaurin series for cosine x. And again, now that you've seen the construction process, you can actually try this first on your own and then pause the video and then resume to see what I come up with and if it matches with yours. So example 5, find the Maclaurin series So find the Maclaurin series for cosine x. All right, so very similar process. But I want to show you an interesting so we learned this in a previous section, right? This is what's kind of cool about power series, is that after you get through the different methodologies, you can come across situations where you can reach or come up with a power series for a problem in many different ways. And what you should do in situations like that is think carefully about which one is going to be the quickest and the easiest for you. So I obviously can go ahead and make a table for cosine and go through that, right? But is there a better way? Is there a way I can tie this cosine to something else that I already know a Maclaurin series for? Yes, you guessed it. It's cosine x is the derivative of sine x. So since I already have a formulation for a power series for sine, I can just derive it. Remember, we did in the previous section, we saw that when you derive a power series, the radius of convergence is not affected. So we already know that sine x is equal to summation n equals 0 to infinity. Do you remember the formula? -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And the expansion will be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and so on. So for cosine x, I'm going to remind myself that that's the derivative of sine x. And if sine x is equal to that Maclaurin series, then the derivative of sine x can be obtained by deriving that Maclaurin series. So I'm going to go ahead and take the derivative of every one of these terms. So what happens? Just use power rule. You get 1 minus 3 x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial. Imagine the next term. What would be the next term? It would be plus 9x to the 8th over 9 factorial, and so on. Now I can simplify these, because remember, 3 factorial is 3 times 2 times 1, or another way of thinking of it is 3 times 2 factorial. So if I have a 3 over 3 factorial, I could cancel the 3's and I'm left with a 2 factorial in the denominator. So this can reduce, and I can write this as 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial, and so on. We just came up with a Maclaurin series for cosine. And we did it in a way without having to build it from the table. Now, there's nothing wrong with using the table. So you could do exactly what we did for sine here and repeat it for cosine, and you'll see that you'll end up with the same answer we got by taking the derivative. Now notice something interesting about this pattern. This pattern actually keeps only the even powers. Think of this as like the 0 power of x. This is like x to the 0, then squared, then 4th, 6th, 8th. Next one will be 10th. It skips all the odd powers. The sign skips all the even powers. All right, so this is again another little test for you. See if you can write the formula for this, the summation notation for this, the sigma notation for this. So again, I would pause the video, try it, and then see if you get the same thing. All right, so if I want to actually end up with even powers, I'm going to take x to the 2n over 2n factorial. Now be careful when you write 2n factorial, you want the whole 2n factorial, like that. Those parentheses are very important. If you remove the parentheses, then you're only doing the factorial of the number n, not the 2 included. So what if you couldn't tell by looking at this what the formula is? You could take this formula and derive it. If you do the power rule here, the 2n plus 1 comes down. It cancels the 2n plus 1. So what's the prior to what's 1 less than 2n plus 1? It'll be 2n factorial, right? So that's going to be 2n factorial x to the 2n, and that matches. So this will be the answer for that example. So that example was actually pretty quick. All right, let's keep going. I know we're a bit. I have a couple more examples to wrap up, and that will take care of this section. And then we're good with this section. So example 6. Find the Maclaurin series for the function f of x equals x cosine x. All right, so here we are again. Always ask yourself, can I build from something else that I already know? Like, can I use another function that I know the power series for as a baseline to get to the one that they want me to find? If you can always find an easy path that way, it's much better than trying to build it from scratch. Why? Why is building it from scratch using the table not always the best option? Well, because you have to find a bunch of derivatives. And if the function is really complicated, this is not very complicated, but the fact that it has a product, it already complicates the derivative, because you have to do product rule. So when you do the first derivative, you're going to do a product rule, right? And then you have to keep deriving. You could do it that way, but there is a better way. So what's the better way? Well, we just did the Maclaurin of cosine. You just need to times it by x, right? Because that's what this function is. This function is the cosine function times x. So that's exactly how we're going to do it. So x cosine x is equal to x times summation n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. And I can bring the x inside. So it becomes summation n equals 0 to infinity, negative 1 to the n. And what happens when you multiply this x by this x to the 2n? You add the exponents. So it becomes x to the 2n plus 1 over 2n quantity factorial. Now, if you actually went through doing the table, I'm not going to go through it carefully, but if you did the table, you would have had to first say, okay, here's my x cosine x function. Then take the derivative of that. So it would be 1 cosine x minus x sine x. So see how ugly that gets? Then you have to take the derivative again. So this part becomes negative sine, and this part you have to do a product rule again and distribute the negative. So you see how ugly that gets? You can actually do all this, and you'll have to do maybe 4 or 5 terms, and you may have to do more than that to see a good to get to a pattern that you can use. And then you're going to replace all the x's with zeros, and then you're going to put the coefficients in, and you'll end up getting exactly the same thing that this gives you. So this is so much nicer. It's a much shorter path to get to the answer than building it directly from scratch. So again, constructing it from scratch using the derivatives is something solid, but it's not always the fastest way. So if you can bypass it by building from something else, by using differentiation or integration or by times in two things, that saves you a lot of time. So always explore other paths before you build it from scratch using the table. That's the moral of the story. All right, let's do the last example. So the last example, example 7, represent f of x equals sine x as the sum of its Taylor series, they didn't say Maclaurin, so they have to give you an a value centered at pi over 3. All right, so now we're out of luck. Why? Because I can't build from a Maclaurin series, right? What I'm going to have to do is I'm going to have to basically do the table, because again, I'm not plugging in 0 here, so I can't use something else. So I'm going to make my table. And I'm just going to, this is not really formal table, but we'll just write f of x is sine x, f prime is cosine x, f double prime is negative sine x, f triple prime is negative cosine x, fourth derivative is negative, is positive sine x, and that's where the cycle starts repeating again, right? So fifth is going to be cosine x, and so on. All right, so now I'm going to plug in, so this corresponds to the nth order derivative, and here I'm going to replace x with pi over 3. So in all of these formulas, I'm going to plug in pi over 3. So sine pi over 3 is going to be radical 3 over 2. Cosine is going to be 1/2. Negative sine is going to be negative radical 3 over 2. Negative cosine is going to be negative 1/2. And then the cycle repeats, right? So radical 3 over 2, 1/2, negative radical 3 over 2, negative 1/2, so on. All right, so based on that, we can actually write the first few terms. And I'm going to have to move to the next page here because I don't have enough room in here. But I'll give you a minute to look at that, to make sense of that table. All right, so let's flip over to the next page. So sine x is equals summation n equals 0 to infinity fn of a, which is pi over 3, times over n factorial times x minus pi over 3 to the n. That's just the formulation of a Taylor series. The only thing different is I replace a with pi over 3. So if I write it in expanded form, this will be f of pi over 3, then plus f prime of pi over 3 over 1 factorial times x minus pi over 3 to the 1, plus f double prime, make sure that's a double prime, pi over 3 over 2 factorial times x minus pi over 3 squared, plus f triple prime of pi over 3 over 3 factorial times x minus pi over 3 cubed, and so on. Now remember, we have a 4 cycle, which means the first term, second, third, fourth, and then after that we have a repeating pattern of what these values are going to be. So we already know the first one is square root of 3 over 2. So the first term is square root of 3 over 2. Then the next one is going to be 1/2 over 1 factorial times x minus pi over 3. And then the next one is going to be the negatives of those two. So it'll be negative square root of 3 over 2 over 2 factorial times x minus pi over 3 squared. Then it's going to be negative 1/2 over 3 factorial times x minus pi over 3 quantity cubed. And then we go from there, right? And that's going to repeat the same cycle. Oops. Not showing you the screen here. Here you go. So all I did is just replace f of pi over 3 with radical 3 over 2, f prime of pi over 3 with 1/2, f double prime of pi over 3 with negative radical 3 over 2, and I put that negative in front. And then f triple prime of pi over 3 is negative 1/2, and I move that negative down. And I can actually do a couple of things here. I can make these fractions nicer to look at, so I can make better sense of the pattern. So this is a radical 3 over 2 plus 1 over 2 times 1 factorial times x minus pi over 3 minus radical 3 over 2 times 2 factorial times x minus pi over 3 squared minus 1 over 2 times 3 factorial times x minus pi over 3 cubed, and so on. Now coming up with a pattern of this is much more challenging. Because notice that in certain situations you've got a 2 here, you got a 1 over 2, you got a 1/2. But every other term you have a square root of 3 over 2 instead. And you also have a sign that flips back and forth between positive and negative. So if somebody actually tried to write one single formula for this, it would be almost impossible to do that. But you could split this into two groups of terms, all the terms that have a 1/2 and all the terms that have the square root of 3/2. And if you do that, you could write it as two separate sums. Summation n equals 0 to infinity, -1 to the n, square root of 3 over 2 times 2n factorial x minus pi/3 to the 2n plus summation n equals 0 to infinity, -1 to the n over 2 times 2n plus 1 factorial times x minus pi/3, the whole thing to the 2n plus 1. So, a couple things, because I know this looks very intimidating. So, a couple important things to keep in mind here. So, first of all, what is this pattern here? How did we get that? Basically, the trick was to notice that when it's an odd power here, that's when you get the 1/2. So if it's like power 1 or power 3, that's when you get 1/2 there. So all the odd powers are going to have the 1/2, the 2 there. So that's 2n plus 1 for the odd power and over 2n plus 1 factorial. And that matches the power. The factorial always matches the power. And you want the sign to switch back and forth. And all the even terms, or even powered terms, are the ones that have the square root of 3/2 pattern, right? So like this one here, and this one, and the power 4, and the power 6, and so on, right? So that's what allowed us to actually split this into two sums, one for the even terms, one for the even powered terms, one for the odd powered terms. But this is not always easy in situations like this to come up with something like that. So a lot of times if you get a problem like this on the exam or exercise where the summation pattern is really complicated, you're typically not going to be expected to give that in that format. You just write the first, I usually will say, give me the first 5 non-zero terms, and you'll just keep it in expanded form. You'll still obviously need to make sure you put the ellipsis symbol, which means it's an infinite sum, but you wouldn't have to come up with something complicated like this, right? But the ones where you are expected to give something, give the pattern, those are like the ones we did earlier where they were much simpler formulas to build the pattern for. All right, folks, so this completes this section, and that's really all I wanted to cover in this video. So again, this is not an easy section, so spend as much time as you need to make sure that you absorb all this, rewind, pause, write down, redo some of these problems, and don't hesitate to let me know if you have any questions. I hope this was helpful, and thank you for watching.